In this video, we will be looking at section 3.6, which covers complex zeros. So we need to start thinking about imaginary and complex numbers. Recall that the imaginary number I is equal to the square root of -1. Any real multiple, sorry, not multiply, but any real multiple of I is also an imaginary number. So something like 3i, -2i, pi I. If you take I times any real number, you also get an imaginary number. Now, when we put a real number added to an imaginary number, we get what's called a complex number. So a complex number is in the form z equals a plus bi. So we have a real number plus an imaginary number. We say that a is the real part of the complex number and b is the imaginary part of the complex number. Now we're going to start by simplifying some of these. So we're going to start by looking at the square root of -25. It wants us to simplify it into a single complex number. So something in the form a plus bi. Since I see the square root of -25, I can break this into the square root of -1 times 25, because -1 times 25 is -25. But then I can break that into the square root of -1 times the square root of 25. We just said that the square root of -1 is I, and we know the square root of 25 is 5. And I times 5 we would write as 5i. We could write 0 plus 5i, but that doesn't really help anything, so we're just going to leave it as 5i. In this next one, we're looking at 4 plus the square root of -20 over 2. So let's start by looking at that square root of -20. The square root of -20 can be thought of as the square root of -1 times the square root of -1 times 20, which I can break into the square root of -1 times the square root of 20. Well, we know that the square root of -1 is I, but what about the square root of 20? Let's see if I can break that down at all. So I'm going to look at the prime factorization of 20. 20 is 4 times 5, and 4 is 2 times 2. I have a pair of 2's, so I can bring them out front, and the 5 does not pair up, so it'll stay under. What I'm saying is the square root of 20 can be written as, I have a pair of 2's, so I bring a 2 out front. The 5 doesn't pair up, it stays under the radical. So looking at the square root of -1 times the square root of 20, we get I from the square root of -1 times 2 times the square root of 5. And we're going to write that as 2i times the square root of 5. In general, the I usually goes last. But when it comes to a term that also has a square root in it, we're going to put the square root last so we don't run into the issue of something like this. If we wrote it as 2 times the square root of 5i, it's hard to tell if the I is under the square root or not, so we write it out front so we don't have that issue. So we're going to rewrite the square root of -20 as 2i times the square root of 5. So we have 4 plus or minus 2i times the square root of 5 all over 2. Now, oh sorry, plus or minus, I'm just so used to the quadratic formula. This is just a plus. Now I can break that up into two fractions. We have 4 over 2 plus 2i times the square root of 5 over 2, and I can reduce those. 4 over 2 is 2. Then we have a plus sign. My 2's cancel, leaving me with I square root of 5. So you get 2 plus I square root of 5. Next up, we're going to look at arithmetic with complex numbers. So we're going to add, subtract, and multiply these, and then we'll do division on the next slide. So we're going to start by adding these. When we are adding complex numbers, just think of it as combining like terms. First, we need to deal with these parentheses, though. Since I don't see anything out front, I'm going to put out some invisible ones, and I'll distribute those through. 1 times 2, 1 times -3i, 1 times -5, 1 times -i. And now if I combine my like terms, 2 minus 5 is negative 3. Negative 3i minus I is a negative 4i. So if I add together those two complex numbers, I end up with negative 3 minus 4i. Now let's try subtracting them. 2 minus 3i minus negative 5 minus I. To deal with the parentheses, I'll put my invisible ones out front, just like I did last time. I'll get 2 minus 3i, but now I have to be careful because I'm distributing a negative 1. Negative 1 times negative 5 is a positive 5, and negative 1 times negative I is a positive I. Now if I combine like terms, 2 plus 5 is 7, negative 3i plus I is negative 2i. So this complex number is 7 minus 2i. Next up, we're going to look at 2 times negative 5 minus I. So I'm just going to distribute that through the parentheses. I'm looking at negative 10 minus 2i. Can't do anything with that, so it just stays. Next up, we're going to distribute a negative 3i through the parentheses. Negative 3i times negative 5 is a positive 15i. And negative 3i times negative I will be a positive 3i squared. Never, ever, 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 never do I want to see an I squared in your answer. Remember that I is equal to the square root of negative 1. So if we have I squared, that's going to be negative 1. Because I squared is going to be the square root of negative 1 squared, which is negative 1. So we need to replace this I squared with a negative 1. So we're looking at 15I plus 3 times negative 1, which is 15I minus 3. Now we typically write our complex numbers with the real part in front, so I'm going to switch these so that the negative 3 comes first, then the positive 15I. In the last one, we're multiplying 2 minus 3i times negative 5 minus I, so we're going to FOIL this out. 2 times negative 5 is negative 10. Outside, 2 times negative I is negative 2i. Inside, negative 3i times negative 5 is a positive 15i. In last terms, negative 3i times negative I is going to be a positive 3i squared. There we go. I'm going to combine like terms, and I'm also going to take care of this I squared. So we have a negative 10. Negative 2i plus 15i is a positive 13i. And then we have plus 3 times I squared is negative 1. So that is going to give us, let's get some more room here, negative 10 plus 13i minus 3, which is negative 13 plus 13i. So we've done addition, we've done subtraction, we've done multiplication. What comes next is division. We're going to simplify each expression into a single complex number, just like we have been. The trick with dividing complex numbers is we do not want an I in a denominator, ever. Not for our final answer, at least. So starting here, we have 8 minus 3i over 4. I don't have an I in the denominator, so I'm just going to split this up into 8 over 4 minus 3i over 4. And 8 over 4 is 2. So I'm looking at 2 minus 3i over 4, which I can write as 3/4 I. That way we can clearly see A plus our B I. Next up, we're looking at 5 plus 2i over 3i. What's going to come into play here is if you have an I in the denominator, we are going to multiply the numerator and denominator by the complex conjugate. The complex conjugate is the same number, A plus BI, but change the sign on the BI term. So A minus BI. Those two are complex conjugates of each other. So when you see an I in a denominator, we're going to multiply numerator and denominator by the complex conjugate. So right now, this is 0 plus 3i. So I'm going to multiply numerator and denominator by 0 minus 3i. So I'm going to multiply it by a negative 3i in the numerator and the denominator. In my numerator, I'm looking at negative 15i minus 6i squared over negative 9i squared. There's a lot going on there, so let's simplify what we've got. We have negative 15i minus 6 times negative 1 over negative 9 times negative 1, which is negative 15i plus 6 over 9. Remember, we want to put the real part first, so I'm going to switch my 6 and negative 15i. I'm looking at 6 minus 15i over 9. If I break that up, that's 6 ninths minus 15 ninths I. And if I reduce my fractions, that's 2/3 minus 5/3 I. Finally, we're looking at 6 plus I over 1 minus 3i. Again, we're going to multiply by the complex conjugate. Right now, we're looking at 1 minus 3i, so the complex conjugate will be 1 plus 3i, because we're just multiplying by the same number, but change the sign on the I term. So I'm going to multiply by 1 plus 3i in both my numerator and denominator. I'm going to have to FOIL both of those. In my numerator, I'm going to get 6 plus I plus 18i plus 3i squared. In my denominator, I'm going to have 1 minus 3i plus 3i minus 9i squared. Let's combine with some like terms. We have 6 plus 19i plus 3 times negative 1. In the denominator, I have 1 minus 3i and plus 3i cancel, so minus 9 times negative 1. So my numerator is 6 plus 19i minus 3. My denominator is 1 plus 9. So I'm looking at 3 plus 19i over 10. And if I break that up, that's going to be 3/10 plus 19/10 I. So that's how we're going to divide our complex numbers. We are always going to make sure that we do not have an I in the denominator. If we do have I somewhere in the denominator, we're going to multiply the numerator and denominator by the complex conjugate of the denominator. We've seen something like this complex factorization theorem before. We just saw it with real numbers, but it's going to work with complex numbers too. If f is a polynomial with real or complex coefficients with degree n is greater than or equal to 1, so we have to have some sort of polynomial with a degree of at least 1, then f has exactly n zeros. So this is what I mentioned in the last one, how if we count up the multiplicities, these zeros could be some combination of real and complex. And again, this counts multiplicities. So if z1, z2, up through zk are the distinct zeros of f with multiplicities m1, m2, up to mk respectively, then f of x equals a times x minus z1 to the m1 times x minus z2 to the m2 up through x minus zk to the mk. So every time we find a zero, we can write x minus that 0 in parentheses, and that will be one of our factors. We have this a value out front like we saw before because there might be some sort of stretch factor that we have to account for. We'll see what we can do. It says to find all of the zeros of the polynomial and then completely factor it over the complex numbers. Let's be really smart about this. Now, we have a graphing calculator at our disposal, so let's see if it can help us at all. In my y equals, I'm going to type in the x cubed minus 4x squared plus 9x minus 10. If I look at my graph, my window seems to be a little off, but I can still see one of these zeros. If I calculate the 0, it looks like it's between 1 and 3. I'm going to guess that it's 2. Yeah, it says that it's 2. So it looks like x equals 2 is one of my zeros. I'm going to double check that with my synthetic division. So my 0 is 2. My coefficients are 1, negative 4, positive 9, negative 10. I bring down the 1, I multiply, I add, I multiply, I add, I multiply, I get a remainder of 0. So what this is saying is x equals 2 is one of my factors. So when I factor this, one of these is going to be x minus 2. When that x minus 2 is factored out, what's left comes from what I see here. The 0 is the remainder. It's gone. We don't care about that. The 5 is our constant. The negative 2 is our x term. The 1 is our x squared term. So what we have is 1x squared minus 2x plus 5. So I know that one of my zeros is x equals 2, but there's 2 more sitting in here. I have to find those. Well, I know how to solve that thing is equal to 0 if I use the quadratic formula. So if we use the quadratic formula, we will have, we're going to hope it fits down here, x equals negative 2, so positive 2, plus or minus the square root of negative 2 squared minus 4 times 1 times 5 all over 2 times our a value of 1. So that's going to be 2 plus or minus the square root of 4 minus 20 is going to be negative 4. Oh, sorry, negative 16. I was getting ahead of myself. All over 2. So that's going to be 2 plus or minus. The square root of negative 16 is 4i. That's all over 2. If I break it up, that's 2 over 2 plus or minus 4i over 2, which is 1 plus or minus 2i. So my other 2 zeros, I guess I can put them up top here, will be x equals 1 plus 2i and x equals 1 minus 2i, because the plus or minus. Those 3 are my zeros. So we already know we have the x minus 2. Now we can factor the x squared minus 2x plus 5 because we're going to have x minus 1 plus 2i and x minus 1 minus 2i. You'll notice I put my complex numbers in parentheses because we're subtracting the whole thing. We are going to have to distribute. So this factors into x minus 2 times x minus 1 minus 2i times x minus 1 plus 2i. That is the factored form of our polynomial, and our zeros are x equals 2, x equals 1 plus 2i, and x equals 1 minus 2i.